Hi, welcome to this presentation on short-term memory in neural language models. What is short-term memory in language? It's the capacity to maintain and access the representations of past context for current processing. For example, in the sentence, "The girls standing at the desk are tall," I need to maintain the information about the grammatical number of the noun girls in order to choose the correct form of the verb, are. We have evidence that neural language models do have short-term memory. They're reasonably good at solving this subject-verb agreement test. They also show success in few-shot learning, that is, when a model has to solve a novel task on the basis of examples given in context. Studying the short-term memory of language models therefore allows us to better understand the nature of their success in natural language processing. Our question is, what is the nature of memory processes that language models learn? Specifically, are these representations explicit verbatim, or are they more implicit and gist-like? We study this by embedding two lists of nouns in short vignettes. These are fed as input sequences to language models. We're then interested in knowing how does language model surprise change on the second list relative to the first list. We call this repeat surprisal. I show you here an example sequence and language model surprise. The two lists are marked in blue. Now, repeat surprisal is simply a median surprise on the second list divided by the median surprise on the first list and expressed as percentage. So a repeat surprisal of 100% indicates no change and hence no memory on the second list. To get a better understanding of the nature of these memory representations, the second list was either repeated, testing for the basic memory effect, permuted, testing for the effect of word order, or novel, to make sure that the model was indeed retrieving the first list from context and not, for example, memorizing it from the training set. Now, to overview the results, when we tested transformer language model across a range of list sizes, we can see that the repeated and permuted lists receive a repeat surprisal of 0 and 50%. Now, these reductions in repeat surprisal indicate memory, and hence the differences across condition indicate that the model representations contain information about word identity and word order. When we tested perplexity-matched LSTM, we could not show a similar effect. Now, in the paper, we report a range of experiments trying to better understand the nature of these effects. For example, we trained the transformer model on a smaller corpus. We see that the effect persists, albeit it is dramatically reduced. Similarly, we tested the LSTM on a simpler paradigm. When the intervening text between the two lists was made very short, we can now see a repeat surprisal reduction of 5 and 10%, a small memory effect, but we did not have evidence that the LSTM representations contain information about word order. Based on these and other results in the paper, we conclude that the transformers implement a high-resolution verbatim short-term memory, whereas the LSTM maintain a core semantic gist of prior lists. We discuss the possible advantages and disadvantages of these two computational systems and the implication for the generalization capacities of neural language models. All in all, the memory paradigm we introduce here allowed us to pinpoint computational differences in the learned short-term memory of neural language models.